You.
Yeah, 17. Oh.
You said -3. Why wouldn't it be like 2?
No, it should be 2. I think what I must have done is there was another graph that I didn't put onto your sheet, and I was reading off of that graph. So yeah, you're right. But if this was meant for this one, then you're right. It should be y equals 2.
And then
So sorry, I think these I realized these are not.
Change some of the other ones too, right?
Hmm?
Because then also
Yeah,
like
you're
21
right.
and 23. Okay.
Right, those are, yeah. So sorry, I realized I did not put the graph for you to read these problems off of. Okay.
Okay, cool. Thank you.
Okay. Yeah, thanks for bringing that up. We're going to continue with our test review. So go to your test review packet. Page 6. We did number 8, right, on page 6. Oh, test review. Okay. Anyone else need a test review packet? So page 6, did we do number 8? Did we do this graph? We didn't? Okay, all right. So let's do the graph, and then we'll do the one below it as well. So this one where that we're going to do very similar things that you did on the quiz, where you have to sketch the graph based off of the characteristics that's provided. But there's something there's something that's new about this graph. Let me just point that out. Now, what's new is A and J here. This is limit as x approaches infinity equals -6, and x approaches infinity, limit is equal to 8. Does anyone know what these are referring to? These are good, horizontal asymptotes. Now, the way that I want you to draw it, so that it doesn't distract from the rest of your graph, is these are just end behaviors, okay? And horizontal asymptotes are end behaviors, meaning that it is just trying to show you how the graph is behaving at the ends of the graph. It's not really impacting the middle of the graph. So this is headed towards -infinity. So that means it's off grid. Off grid, the graph is going to flatten out at -6. So I would go to -6, okay, put a dotted line, but only put a dotted line at the edge of the graph. Don't put the dotted line all the way through. I mean, it's not wrong if you do a dotted line all the way through. I'm just worried that if you do a dotted line all the way through, it may impact how the way you graph it, and it may throw you off. So just know that the dotted line is only really impacting, it's only kind of guiding the graph off grid. It's really not it's not really a line that's going to mean the graph is a restriction, right? It's not a restriction. It is only merely a guide. So we just know that the graph is going to do this. It's going to flatten out towards -6. So if you see a horizontal asymptote, just put a dotted line at the edge, and that way that dotted line won't distract you from the rest of your graph. Same thing here. If we're approaching positive infinity, our graph is going to flatten out at 8. So just go to y equals 8, put a dotted line. You can put it above or below. I'm just going to put it below here. And it's going to flatten out. And then don't extend that dotted line past the edges. All right, so I'm going to have us try the rest of the properties. Order pairs are the easiest to start with. Anything dealing with limits, my preference is I like to just put a hole at that point, and then that way I don't have to. That way it's safer, because then I don't have to worry about maybe I got to erase that point later on because it's going to fail a vertical line test. But if that hole is filled in and it doesn't impact the rest of the graph, then it's fine. I just like holes. It just feels like there's less room for mistakes that way. And then again, if you see it does not exist, there are three things that are available to you. You can either make it an endpoint, you can make it a jump discontinuity, or you can make it a vertical asymptote in any direction that you want, either both positive or one negative, one positive. Okay, so spend a minute, sketch your graph. There is room for interpretation, so some parts of the graph may look different than mine, which is fine. And then after you do 8, we'll try 9 as well. I have the key attached, but I'll also work the problem through as you guys try it. I made mine an endpoint, but you could have something a little different at 0.
Does the hole at -2 have to be a hole? Or can it be?
Right here, you mean?
Yeah.
I like to have it as Starbucks as a whole, but in this case, looks like there's no other conflict, so you can have that filled in and that's fine.
I meant the one at -2, sorry. As X purchase -2, where there's one.
Oh, this one here.
Yeah.
Yeah, I left that as whole, but
Okay.
again, no conflict, so you can have that filled in.
Isn't the or G, wouldn't there need to be another line?
It's only asking for 3 from the right, so you can definitely extend it and not have any issues.
Okay.
This only required 3 from the right, so I didn't even pick up the other side.
Would it be fine if, like, we had like a fragment extend out under like a hole at 0, 0?
Yeah, you can. Yeah, so if that, then you're doing a vertical continuity, which is fine as well. So if you had this extension, that's fine. Yeah,
You also have it as vertical asymptote.
yeah, you can also have vertical asymptote. Yeah, yeah. So few things you can do here for that and be okay. All right, try number 9. I'll make sure that we're comfortable with the inclusion of horizontal asymptotes. Any questions with 9?
Does C have to be a jumpless continuity?
No, you have, you can make it an endpoint, you can make it a vertical asymptote.
So I could do like a vertical asymptote with a point on it.
Yeah, I can do that. All right, if you can turn to page 25 for a moment, I just want to highlight what you can expect on Wednesday's test. So here are a list of test topics, again, page 25. All right, let me just read through these topics here. So evaluating limits algebraically, whether it's a real number approaching infinity, one-sided limit. So I think we've been practicing quite a few of that on Friday, where we know that if we're approaching a real number, we always do direct substitution. If we see infinity, we're always comparing degrees, and we're always making sure that we're staying true with our first steps, that we don't get sidetracked with decimals unless there's a vertical asymptote. We don't get sidetracked with plugging in 100 unless we realize the degree in the numerator is higher. Evaluating limits with hole in the graph. So applying methods of factoring, conjugate, common denominator. These are quiz topics. Those showed good good process there. We practiced these types of problems on Friday as well. Identifying limits to order pairs from a graph. So that was on the quiz where you're given a graph that's filled out and you're asked about limit, you're asked about order pair, and then sketching your graph given limit properties. We just did that, 8 and 9. Use continuity conditions with piecewise function to determine continuity and discontinuity and categorize the type of discontinuity by walking through each of our conditions, order pair, limit, and evaluating or comparing between first and second condition as a third condition. Oh, I do want to point out real quick here, in continuity conditions, this was a question on the morning review this morning, is notation. So I just want to show you real quick here. No, I don't want you to write this down. I just want to look at this here. A problem like this, right, where you're asked to find is there continuity, and if not, what type of discontinuity there is. And our first step is always order pair. Our second step is always evaluating limits. In this case, my one-sided limits are not in agreement, so therefore a limit does not exist, right? And this is more of a notation. Just a comment about notation. When you write your one-sided limit, make sure that you include your expression, right? And if you want to talk about limit and you don't want to write the expression, you got to at least put something there as fx, right? This would be incorrect notation, even though this is the way we say it, right? Approaching 3 from the left is 8. Approaching 3 from the right is 4. The limit does not exist. I know this is the way that we say it, but this would not be correct notation because you're leaving stuff out of this space. So just want to make sure that we're understanding what is correct notation and what is incomplete notation. Okay. Applying intermediate value theorem to guarantee of values. So we'll practice one of those problems today in class, where we have to first establish continuity, and then we test the endpoints to see if both endpoints are on opposite sides of our y value that we're looking for, and then we have to write out our because statements to justify it. Finding horizontal asymptotes. This is where there's a radical in the denominator, and we just do the limit as x approaches infinity, and we just know it's the ratio of the coefficients, but it's plus and minus. So we have two horizontal asymptotes. So in this case, this one will be y equals 3 over root 5, and y equals 3 over negative root 5. So and then comparative growth rates, this is where we have to look at the relationship between logs, radicals, polynomial, and exponential, and decide which is growing faster, above or below. Logs is slowest, radicals is next slowest, then polynomial, algebraic, and then exponential. So if the faster one is up top, then you plug in infinity, then you know it's going to either go to infinity or negative infinity, and you test 100. If the faster one is below and the slower one is above, then the fraction is getting smaller and it's going to be equal to 0. So with comparative growth rates, it's always going to be 0 or plus or minus infinity, just deciding between those two options.
Will it ever be the same, like exponential or exponential?
If it were, then you just take the ratio of the coefficients.
Okay.
Yeah, so probably won't give a problem like this, but like this, if I had like, 3e to the 2x over 5e to the 2x, then that's just going to be equal to 3/5. Yeah, and also you won't need limits here because these just cancel out. So this is being 3.
That only happens if it goes towards infinity or negative.
Yeah, yeah.
We won't have any squeeze theorem on this.
Yeah, good question. No squeeze theorem on the test for Friday. Sorry, Friday, Wednesday. All right, let's go to page 11. And yeah, we're going to practice some of these things that we haven't talked about on, that we didn't quite go through on Friday. So page 11. All right, you got a piecewise function. You're going through, you're evaluating your limits. Again, let's just make sure that we understand what we're looking at here. What is this right here? That's just a what on the graph? Just a point, right? So we know that our limits do not follow our point. So if we're evaluating limits, you never want to look at that middle information here. This is, so limits does not apply. It applies for ordered pairs, but it's not going to guide our limit statement. Okay, so go ahead and try this, and I'll work through at the same time that you guys are working through it as well. If you're working ahead of me, you can always check the key on the back page, page 12, to check your progress.
Test if it's the same degree, right?
I'm sorry,
You only test if it's the same degree, right? Or,
you mean for part A?
no, now that we're testing like -4.1.
Uh,
Like 9 minus x cubed over x squared, would you also still test?
well, you only care about the signs, right?
Yeah.
Yeah, so if it was 9 minus 4.1 cubed, this would be, it'll probably still be a positive, but this,
I'm talking about like degrees.
oh, degrees.
Like if it's a different degree on the top than on the bottom, you still plug in like -4.1.
Yes, yeah. If you're considering like comparing degrees, remember that's only for infinity. Right, we don't compare degrees if it's a real number. So part A, number one, limit as x approaches -4 from the left side of -4. That's the first piecewise. So you put that expression down. Remember, the first thing we do with a real number is we always do direct substitution. We don't do anything with decimals because we don't know what's going on yet. Direct substitution will give us a visual idea of what's happening. So this is an indication there's a vertical asymptote. The limit doesn't exist. And now that we know we're talking about a vertical asymptote and we're approaching that vertical asymptote from the left side, now we know we're down to two options, right? Either the graph is going to shoot up towards infinity when it hits that wall, or it's going to go down to infinity as it hits that vertical asymptote wall. So I'm going to test -4.1 into the numerator. I get a negative, and then denominator -4.1. We know 4 squared is 16, so 4.1 squared is a little bit more than 16. So that's going to keep maintaining that positive value. Negative over positive is negative. So now for part B, we're approaching a negative infinity. And what's the first thing we do if we're approaching a negative or positive infinity? Say it again. Degrees. Check degrees. Yeah, check degrees, right? No negative 100, right? We don't do that unless degree is higher up top. So degrees are the same. So therefore, there is a ratio, there's a limit, which is what? There's -1, right? You got that x squared that's guiding your limit. There's a 1, there's -1 up top, there's a 1 below, so -1 over 1. What do you do if we're just doing limit as approaches -4? Right, yeah, it does not exist. We don't look at that middle, right? This one is not going to help do anything. We gotta look at the left and right because the graph is split on either side of -4. But conveniently, we already have that data that we need. So A and C is indicating that left and right are not in agreement. So we know the limit doesn't exist.
Because the numerator first right now.
Part E, limit as x approaches infinity. So we're back to infinity here. What's our first step? Compare degrees. What do you notice? Yep, higher degree in the numerator, which means that this fraction is doing what? Yeah, you know it's going to either it's going to increase or decrease without bound. So now that you're down to two options, now we can do what?
Plug in 100.
Yeah, now you can plug in 100 because we're headed to the right. So you want to plug a number in the direction that you're headed. So this one I would test 100.
Would you plug in negative 100 if it was going to the left?
Yeah. If it was negative infinity and the degree is higher up top, then I would plug in negative 100 and let that guide my answer. But you only do that if you first compare degrees and realize the top is higher. Yeah.
Could you explain on part B why it just becomes -1 over +1?
Good. So we know if we're approaching positive infinity, we're going to be comparing degrees, right? Degrees match. So if degrees match, I mean, there's a horizontal asymptote. Now there's a number, and we're looking at the x squared now. So now we're just focused on the number in front of the x squared. So there's a hidden one or hidden -1 in front, and there's a 1 in front of the x squared. So it's -1 over 1. So -1. Okay. Part B is asking for, is there continuity or discontinuity at x equals -4? So we're just going to walk through our conditions and prove that if there's the discontinuity, whether it's removable or whether it's non-removable. Okay, so for part B, which is relying on the same piecewise function, but for a continuity condition. Okay, so step through your conditions. Order pair, limits. We can just pull the data that we've already gathered. Part C, find horizontal asymptotes. This is one of the strange ones with the radical. So any questions with part B, number 1? So we know horizontal asymptotes is n behavior. So if we just do limit as we approach infinity, we can at least get one of the coefficients or one of the ratios here. Okay, so we know we're comparing degrees. What do you notice when you compare degrees? Same. So we know ratio of the coefficients is our limit, which is what? 1 over Good, right. √4, which is -1 over 2. I found one of them. I know that there's two of them, right?
Yeah.
If there's an asymptote that's -1/2, there must also be what?
1/2.
+1/2. So you just say horizontal asymptotes at y is equal to 1/2 and y equals 3.
Again, it's the reason there's a horizontal asymptote that both.
This graph looks strange here because graph may look something like this. As it heads to the right, it's flattening out at -1/2. As it heads to the left, it's flattening out at a +1/2. See, but this graph only appears when it's this scenario where there's a radical either above or below and the degrees are the same. Then you know they're it's the ratio of the coefficients, but it's plus or minus.
Would we get a problem where the degree on top is higher than the degree on bottom?
No. Not for these types of problems. Right, number 3. We're going to go through our intermediate value theorem, which is test for continuity and then test endpoints and see if our target endpoint, our target y value 2 is going to land between the endpoints. So our first step is establishing continuity or establishing whether there is continuity. But is there a red flag with this function? What do we have to consider before we just write, oh, function is continuous? There is a what? Yep, and there is basically discontinuity, right? There's a denominator variable. Okay, don't have to worry about whether it's an asymptote or a whole. It's going to be in the same place. Look in the denominator and see if that denominator is going to interfere with the interval. So there's a discontinuity at x equals 3. To set the denominator equal to 0. Is that going to interfere with my interval?
No.
No. So we're safe, right? The only discontinuity is clearly outside the interval. So we've established no issues with continuity. We're going to state our continuity condition now. Make sure you specify your interval. All right, what's our next step?
That's the endpoint.
Test endpoints, yeah. See what the endpoints give us. And we're looking for something very specific from the endpoints, right? We're looking for an endpoint that's higher than 2 and the other endpoint to be lower than 2. Does it matter which one is which?
No.
Yeah. As long as we have one of each. Doesn't matter if you start lower and end up higher or whether you start higher and end up lower. We should need one of each. Eight fifths, 8/4 is 2. So 8/5 is going to be a little bit less than 2. Right, so it's like 1 point something, right? 0.5, 1.6 doesn't, but we know that that's enough. We don't have to know the exact decimal value. We know it's enough to confirm, okay, 2 is clearly between 4 and 8/5. So we're good. We know that we can guarantee that value. So let's go ahead and write our statement. We can say by IVT, since we have one endpoint, which is, I'm going to start with the lower one, f of 8 is 8/5, and 8/5 is clearly less than 2, and 2 is clearly less than my other endpoint, which is 4 coming from f of 4. There must be a C value where f of C is equal to 2 on the interval from 4 to 8. And then it's also asking for the C value. So now we just have to set these functions equal to each other. The function equal to the Y value, cross multiply, solve for X. And we're looking for a C value from there. I'm going to force a 1 below my denominator here, cross multiply and solve for X. Is that safely inside my interval? Yes, right. 6 is safely inside my interval. I don't have to remove anything. That's my solution.
What would that be?
Because this is my X value solution. My C is my X. So X, my 6 is between X value of 4 and X value of 8.
You cross one?
Yeah, I cross multiply. I said 2x equals 2x minus 6. And I added like terms, combined like terms to solve for X. All right, take a look at number 4. Now we're just, this is like a quiz like problem where you're just looking at a graph and identifying either limits or order pair. In this case, I think they're all limits. Any questions? Let's go to page 18 and let's just do more continuity conditions here. So page 18. Okay, go through your continuity conditions. Try number 2, 3. And then the key is on 19. You can check your progress once you've You don't have to include this statement here. You can jump directly from this result to this conclusion. Try number 3. What's different about number 3 versus 2 in terms of your limit statement? Number 3, we only need what? One limit statement. There's no need for one side of limit. We're not split on either side of our target. It's all contained within this. So all you need is one limit statement. And we know this is just order pair. That order pair is not going to have any impact for our limit statement. Oops, equals. Make sure that when you get to the third statement that you're writing out your function limit notation and not just say, oh, 3 doesn't equal to -2. This is what I'm looking for as your justification that we're dealing with a removal based on 3. Yeah.
If it says G of X over there, what we write after that.
Oh, my bad. Yeah, that's my bad. I won't, yeah, because I'm not. No, it should be G, but if you did F, I would understand. I did it too. Okay, hopefully you guys are feeling more and more comfortable as we get closer towards our test date. We still have tomorrow to do another day of review, so but I will be available tomorrow morning for any individual questions. But I'll state that last morning review or sheet for now. Homework, I'm not gonna assign any homework. I just want to check the pages that we've done up to this point. So tomorrow, I'm just gonna check pages in your review. 1 through 12. But you guys have all done it in class, so you should really have to do additional work if you want to get some of it back. Okay. The page 1 through 12.
We just do.
Which ones do we not do?
At the end of page 5, top of page 6.
No, you don't have to. Just the one ones we did in class, and I'll be happy with that. No. I'm going to just check your review packet 1 through 12.
Show up. Practice. If there's nobody on.